Good morning, everyone. Can somebody confirm if you are all hearing me clearly? Is everyone hearing me clearly?
Yes.
Okay. Thank you so much. Thank you for confirming that. Uh, I want to welcome you to my lecture today. Of course, we're meeting on Zoom today because of extreme weather. In my area is -20, and around the University of Minnesota, shall be around that same number. So, when you're going to be outside today, make sure you stay warm. So, this is the second lecture of the spring 2026 semester. And of course, our focus today will actually be on tension in explaining and predicting. Okay, before I get started, in case you want to you get stuck or you want to seek for clarification, of course you can ask me a question. I want today's class to be interactive, just like the way we normally have it in the in-person. So make sure you ask your question. So I want to welcome you to this lecture called Attentions in Explaining and predicting. I remember I said in the last class that before you can actually choose an appropriate model or algorithm, you need to for first, uh, you know, tell her, you need to disclose your intention. So we got difference between explaining and predicting, and that's why today I actually want to walk you through the kind of tensions we have observed between the two. Okay, so in the outline, I'm going to talk about, well, like I said, to explain or predict, uh, walk you through the tensions and how do we actually strike a balance between interpretability and predictive power. Okay, so I need you to pay attention, like I said. Let's get started. Okay, now, the very first question uh, that we that we actually I want to ask is why statistical explanatory modeling differs from predictive modeling. I remember in the last class I talked about uh, statistical modeling. I talked about predictive modeling. Okay, so why are they different? Why they differ? From each other. So that's why I want to first want to shed more light on them. They are different because they are attacking different goals. I'm going to say that again. So the difference exists because the two of them, they actually want to answer different scientific questions. That's why the two models are not the same. So I'm going to talk about uh, this different from the way they generalize. Okay. So when we want to talk about statistical explanatory modeling, okay, before you can use statistical explanatory modeling or model, it means you're actually pursuing an explanatory goal. Okay, your goal is an explanatory. Your goal is to explain. Your goal is actually causal. Okay, so and what we normally do within the statistical framework, we normally collect our data. We take a sample from the population, okay, which is few individuals, few observations, and the generalization, okay, we normally generalize, from the sample to population. We work on the sample and we generalize results on the entire population. Okay, so that's exactly what we mean, when we use statistical explanatory uh, model. So we try to say we actually want the model to perform, well on the, we work on the sample and using what I call inferential procedure in statistics, we're actually going to generalize on the entire population. Okay. So, and the core question that we normally ask, okay, is actually what is the relationship between variables in the population? If you want to answer a question that has to do with what is the relationship between variables in the population, then you need to first look into the variable, the relationship in the variable in the sample. Okay. And from there, we generalize from sample to the population. And that's why we normally see this in statistics, where we specify our model, we actually estimate parameters in the model, we conduct hypothesis testing, and in general, we have a way to quantify uncertainty. Okay, and I also want to believe you heard about confidence interval, all of that actually fall within the framework of explanatory model. Okay, so the generalization that's involved in the explanatory model is from sample to population. But what about predictive model? Okay, how do they generalize in predictive model? Okay, using predictive model. Okay, so the generalization is to set of new individuals. I'm going to say that again. They are generalizing to a new set of individuals. And that is what we normally call the out of sample. Okay, predictive generalization. You actually want to generalize to to individuals that was not even parts of your data set initially. And we have a core question here. The core question is, if I see a new individual tomorrow, will my model give a good prediction? Okay. It's just like you have a model that you've already trained on some data. Okay. You've trained a model on some data, and you now want to use the model to predict a new, characteristic that has to do for a new individual. Okay. So the generalization is not the same. So the bottom line is to answer the reason why statistical explanatory model, differ from predictive model is because they are attacking different scientific goals. And the way they generalize is not the same. Okay, the explanatory statistical model generalized from sample to population, and why the predictive model generalized to a new set of individual. And I just wanted to take note of that. And when it comes to validation, okay, maybe if you want to validate, like you actually want to know how good is a statistical model or how good is a predictive model, okay, you actually going to use a different metric of evaluation, okay? You're not going to use the same because the two are not the same, okay? So I remember when you are validating statistical model, we normally go through statistical inference. Okay, we normally go through statistical inference. The statistical inference is when you're trying to test hypothesis or when you try to construct a confidence interval. Okay, but when you want to validate the predictive model, we normally go by way of cross-validation that we're still going to talk about in this course. So because the two models are actually attacking or two different scientific goal, we're also going to have we're going to have different validation or metric of evaluation. Okay. So before I leave this particular question, because it's very, very crucial, I'm actually going to say the explanatory modeling generalizes from a sample to a population, while predictive modeling generalizes from observed individuals to unseen individuals. There's a difference between the two. Okay, I want to go, I think I've already mentioned this. Uh, the reason why explanatory model and predictive model, the reason why they are not the same is because they are actually apply to actualize different scientific goal, okay, before you can use explanatory model. So it means you actually want to answer a question that has to do with relationship, how one variable affects or influence the other, how one variable causes the other. Okay. So with that, we're going to make use of explanatory model. And that's why you can see here, I said to test. Okay, quantify causal effects. Okay, for average record in the population. And let me tell you this, whenever you are using explanatory model, okay, we are always we're interested in quantifying the causal effect, not for individual level, but for group level. And that's why the average is involved. Okay. Before moving forward, is there any question? I need someone to confirm again, if you are hearing me clearly. Is everyone still hearing me clearly?
Yeah.
Thank you so much. Okay, so like I said, for predictive model, we actually want to predict new individual observations, okay, unseen individual. Okay, we only have access to the observed individuals, but we actually want to use the model to predict for unseen individual. Just wanted to take note of that. Now, let's now come to tensions in explaining or predicting. And I think I've identified five. Now I'm going to explain one at a time. Okay. I just want to tell you, when I say tension, so what actually distinguish between explaining and predicting. Number one is theory versus data. I'm going to explain how that can distinguish between, can explain the tension between explaining or predicting. I'm also going to talk about causation versus association. I'm going to talk about retrospective versus prospective. I'm going to talk about individual versus average record. Then I'm going to talk about bias versus variance. Okay, so these are very, very crucial in explaining tensions or tensions in explanation and prediction. I want to start with theory versus data, and I need you to pay attention. Okay, now, if your goal is a course, if you have a causal goal, if your goal is explanation, okay, the emphasis is more on theory. I'm going to say that again, not on data. The emphasis is more on theory. And you know why? In scientific community, statistician, economists, physics, psychology, sociologists, and so on like that, they normally specify model, and that very model is actually uh, formulated based on theory. Okay, so the emphasis is more on theory. Okay, even though they use data, but the data is just to spice that, it's just they use data in a less formal way, just to spice that. And let me tell you this, uh, if the emphasis is more on the theory, okay, uh, the way the model is now going to be used, the way the explanatory model is actually going to be constructed, is actually going to be constructed in a way that will support interpreting the estimated relationship, okay, between X and Y. So initially, before they specify their model, they believe they assume relationship exists between the variables under investigation. And if you take a look at F here, okay, you can see two type of F that I put here, and I need you to pay attention. Okay, give me 1 second. I'm actually if you take a look at this guy, this particular F, okay, that is the true data generating mechanism, that link X with Y. Okay, there's unknown that we want to figure out the true relationship. okay, that we want to figure out. But you know what? This particular F is actually the statistical model, okay, that we specify, okay, that we want to use to estimate this guy. Okay, the statistical mode. This particular guy here is actually the true relationship, okay, that exists between the variables under investigation. But this particular have here is actually the statistical model that we actually put forward, okay, that we put forward uh, to estimate the true relationship. And what I'm trying to talk about right now is that the way this particular statistical model have is specified, we normally specify that in advance. Okay, and that's why I said the other time. Okay, statisticians, physicists, chemists, biologists, everyone in scientific community, the emphasis is more on the theory. Okay, because they actually and the theory will guide them in specifying the statistical or the model. Okay, and of course, like I said, that particular have is actually carefully specified in advance, based on scientific theory, based on subject matter knowledge and assumptions on how X influences Y. But on the other hand, when you look into predictive modeling, the way we construct statistical model is different. Okay. The way we construct statistical model here, okay, is we actually constructed that from the data because the emphasis is going to be more on the data and they're actually going to use theory in a less formal way. So when you are using a predictive model, okay, the emphasis is more on the data, not on the theory. But in the explanatory model, the emphasis is more on the theory. Okay, I just wanted to say that. So what I'm trying to say here, okay, the direct interpretability in terms of the relationship is immaterial, it's not really required, okay, because the predictive model, the intention is actually to predict unseen individuals. Okay, so I just wanted to understand that. Okay, now the bottom line, okay, in explanatory model, okay, if you take a look at the explanatory model, the statistical model that I talk about is designed to approximate F in a way that support interpretation, okay, and testing the cursor. You actually have something in mind that you actually want to test. But in the case of the predictive model, the way the goal is to accurately predict, okay, for new record, new observations. Okay, they are not interested in explaining why maybe S causes Y. They're not interested in that. Okay, I believe you understand the distinction between the two. Now, I want to go into causation and association. Okay. Now, if I on the issue of causation and the association, okay, the way we construct our statistical model, which is the way we construct, take a look at this guy now. Okay, this is what we mean by the model. F is a model. Okay, so if your goal is explanatory, if your goal is causal, okay, the health is going to be constructed in a way, okay, there's going to be an assumption that that particular health actually represents an underlying causal function, okay. An assumption is going to be, oh, S is assumed to cause Y. Okay, maybe S is let me just say smoking. Maybe I'm looking at the effect of smoking on the risk of getting cancer. Okay, so assumption is going to be from the one using explanatory model that smoking is assumed to cause the response variable of interest. That is the that is that. But in the case of predictive model, okay, uh, with regard to causation and association, okay, the way we construct F, F does not actually capture or underlying causal function. It doesn't actually assume any, it doesn't assume that a particular variable influence the other, but it only capture association. And I need you to pay attention now. What is the difference between causation and association? Okay, there's possibility two variables may be associated, no, they may be into association, okay? They may be related, but that doesn't mean one causes the other. Okay, I can give you an example. Okay, so when I look into a relationship between uh maybe the sales of ice cream, the sales of ice cream and crime rates. Okay, if the relationship exists, that doesn't mean the sales of ice cream actually cause criminality. So causation is not as association does not imply causation. I'm going to say that again. Association does not actually imply causation. Okay, and we got a reason why we say that. Okay, association does not imply causation. So I'm actually gonna say this again. Okay, when you are using explanatory model, okay, the way assumption there is that based on the underlying scientific theory, assumption is that S is assumed to cause Y. Okay, so that is the assumption, and we specify our model to investigate, to test that causal effect. Okay, and that's what we do. Mostly, that's what we do is statistical, community. That's what we do. Now, for the predictive model I just talked about, okay, when a correlation exists, okay, because that's an association. That doesn't mean uh the relationship that exists cannot, this can be translated into causation unless something is done. Okay, because as time goes on, I'm actually going to tell you what can we do to translate association into causation. Okay, that can be done. Okay, but I'm just trying to tell you right now that the difference that exists between the two, okay, in terms of causation and association, okay, when I'm using statistical explanatory model, of course I'm actually pursuing a causal goal. Okay, I'm actually assuming that, oh, okay, or this particular, there's something that we call cause and effect. So this particular variable causes the other one. When I'm using the predictive model, okay, that only capture association. Association is relationship, and that doesn't mean when relationship exists, that doesn't mean the other variable causes the other. Okay, so that is the causation and association, which is the channel attention. Now, I want to go into retrospective and perspective. Okay, and I need you to pay attention now. Okay, I'm going to say this. When you are seeking an explanatory goal, when your goal is causal goal, when your goal is to explain why things happen, with your goal is to explain how a particular variable causes the other variable, okay, you're actually going to go retrospective. Retrospective is looking backward. I'm going to say that again. Retrospective is actually looking backward. Okay, so what do I mean by looking backward? We are actually looking backward from the data to evaluate the theory. Don't forget, we got the theory. The theory will enable us to put in place our model in the first place. Okay, the model is specified ahead of the data. So when you have your model in place and you collect your data, okay, then we're actually looking backward. That's what we call retrospective. So which means, don't forget, you specify your model first based on scientific theory, and after that, then you conduct an hypothesis testing and inference. And why are you doing that? Because you actually want to explain relationship, okay, that are believed to already exist. Nobody in scientific community go into research with an empty mind. There's something they really want to confirm. Okay, so that is what I mean here. So the way the F is used, that very F, that statistical model F is used to test the hypothesis that we already put in place. Okay, but when you take a look at the predictive modeling, on the other hand, the predictive modeling, on the other hand, is not looking backward, it's looking forward. I'm going to say that again. Because when you are using predictive model, don't forget, you are interested in predicting future. You are interested in predicting new individual. You are not interested in the past. You are not interested in how a particular variable causes the other. That is not your intention using predictive mode. And that is why it is prospective. Okay, that is why it is looking forward, and that is why the your statistical model have is actually will be constructed for predicting new observations, which I call the unseen individual. Okay, so I just wanted to take note of that. And let me now tell you this. I want to differentiate again between F, the F that I mentioned here, the statistical model here, F, and the F here. And I need you to pay attention. I'm actually going to differentiate that again. Okay, so when your goal is explanatory, when your goal is Cosa goal, which means you actually want to investigate why. Okay, you want to investigate how a particular variable causes the other. The way you're going to construct your have, okay, you actually going to construct your have in a way that you want to test hypotheses that are already in existence. And that is why in statistics, you're gonna see us computing p-values. Okay, we normally compute p-values because with p-values we can actually test the significance of a particular effect. Okay, we do that all the time. Okay, in statistics. But let me tell you this: the way we construct have when we have a predictive goal, okay, is different. Okay, the health is constructed here to predict unseen observation, future observation. Okay, and let me tell you the way the health is done. Okay, we are not going to using predictive model. We're not going to specify the health in advance. We're actually going to learn that model from the data. I'm going to say that again. In predictive model, F is learned from the data. Okay, we're going to learn F from the data. Okay, and we're actually going to arrive at a particular one with a minimal loss function. Okay, with a minimal loss function. Just wanted to take note of that. So the model performance is evaluated on the new data. Okay, not on how well it explained the past observations. I just wanted to see the difference between the two. Before moving forward, can you confirm me? Can somebody confirm again if you are still hearing me clearly? Is everyone still hearing me?
Yep.
Thank you so much. And thank you for confirming that. Okay, so before moving out of here, moving from this slide to the next slide, I'm actually gonna say explanatory modeling is retrospective, that is looking backward, using the data to test pre-specified hypotheses. Okay, why predictive modeling is prospective, and what I mean by prospective is looking forward. Okay, where the interest is actually forecasting future outcomes. Okay, we want to predict future outcome. We want to predict unseen record. Okay, so another tension in explaining and predicting. Okay, so when your goal is explanatory, when your goal is COSA, okay, emphasis is more on the average. And that's why in statistics, you're going to hear us talking about average treatment effect, average this, average that. Okay. So, using explanatory model, we actually seeking generalizable insight by averaging over many observations. So the power of average is huge. So when your goal is explanatory, okay, let me tell you this. When you are looking into relationship between variables, okay, you are looking into that, you're trying to say, okay, uh, on average, okay, I remember when you are interpreting linear regression, regression coefficient, your linear regression coefficient, for for instance, if you are actually looking into the effects of study hours on exam performance, and you specify the model and you estimate the regression model, and you now want to interpret the slope. You're going to say, oh, for every unit increase in our study on average, the value, the exam performance increases by that. You can see you mentioned an average. So emphasis is more on the average when we are seeking explanatory goal. But when you are seeking predictive goal, emphasis we don't make prediction at group level. Okay, we are interested in individual. We're interested in individual, not at group level. Okay, so predictive model target precision in predicting each individual observation, not group. I just wanted to see the difference. When you are seeking explanatory goal, okay, emphasis is going to be more on the average. When you are seeking predictive goal, emphasis will be more on the individual. But let me tell you this. Do you know what is going to be gainful to scientific community? Can we also have a way to explain at individual level? Can we also have a way to predict at a group level? That would be gainful to scientific community. But right now, the explanation is done at group level, and that's why average is involved. Predictive, prediction is done at individual level. Okay. Now, I want to go to the last tension, that we call bias and variance, and I need you to pay attention. Okay. Now, when I say bias, what do we mean by bias? Okay. Bias is actually the result of misspecifying your model. Okay. When you are seeking an explanatory goal, we normally specify statistician, economists, biologists, chemists, psychologists, and everyone in scientific community. When they are seeking explanatory goal, they normally specify their model in advance. Okay. When they specify wrong model, okay, then bias arise. So bias arises as a result of model misspecification. Okay, so the worst enemy of everyone in scientific community is bias. I'm going to say that again. The worst enemy of a statistician, the worst enemy of economists, the worst enemy of everyone in a scientific community is bias. Okay, they normally want to try and reduce bias, even though bias cannot be completely eliminated. But let me tell you this, what we do in scientific community when to reduce bias is to add more variables to the model. When you add more variables to the model, okay, even though they're going to succeed in reducing bias, but they're actually going to create additional problem, and which we call the problem of high variance. It is the high variance that talk about the sensitivity of your model to new observation. If you use a new subset of training data, your model will respond rapidly, okay, to that. Okay, high variance is not good. The high variance is as a result of over parameterization. Okay, it's actually going to make your model to overfit. Your model is going to overfit because you got so many variables in your model. You know why you got a lot of variables in your model in the first place? Because you actually want to reduce bias. And that's why you are adding more variables to your model. And when you add more variables to your model, if there's a lot of variables in your model will suffer, your model will capture noise. Even though your model is going to perform greatly on training data, but your model will perform poorly on unseen data. Your model is not going to be good for generalization. And that is the reason why we need to seek for a trade-off between bias and variance. And if I'm seeking explanatory goal or I'm seeking predictive goal, specifically when I'm seeking predictive goal, there's something that we call the expected prediction error for a new observation. Okay, if I really want to know whether my model is fantastic, then I need to compute what I call expected prediction error for a new observation. And this is going to look in form of a quadratic loss function. And I want to explain this. EPE means expected prediction error. Okay. Now, why here is a reality? Okay. And why this is actually the estimated reality. That's why it's having a cap. Estimated reality. Okay. Now, when I decompose this, we decompose this into three components, which I'm actually going to explain. If you don't understand, ask me a question. I'm actually going to start from this. Do you know that guy is actually the error that we normally going to have, even if your model is correctly specified, there's always going to be error. Whether your model is specified correctly or your model is not specified correctly, there's always going to be error. You remember I told you from when in my first class, I told you that even though we want to use some model to depict reality, model cannot give us exact characterization of reality. There's always going to be a loss. Okay, the variance of y here is actually the error that is inherent. Okay, on the model, whether it is correctly specified or not. Okay, so the second, and what we're trying to do is to try to minimize that. But the second part that I call a bias, okay, is this actually arise as a result of model misspecification. When you misspecify your model, when I say models misspecification, you know what I mean? Whether maybe you misspecify the functional form of your model, maybe your model is supposed to be non-linear, you specify linear. Okay? Or your mode is supposed to be linear, or you specify non-linear. That's what I mean. Or an important variable is missing in your model. Or, a nuisance variable is present in your model. That's what we call bias. Okay? Bias arises as a result of model misspecification. Okay? Now, let's talk about the third one. Okay? Now, this very third one, okay, the fact that you are using sample, okay, the fact that you are using sample, okay, to estimate the target function, then that is the error that arise. Okay, that's why you say the variance of the estimated function. Okay, and that arise when you are using sample. Don't forget, in research, we do not have enough resources to study everybody in the population. We normally take a sample. Okay, don't forget we are limited by budget. Okay, so of course, the fact that you are using a sample data, not the entire data set, to estimate the target function, because the target function is f. So the f, also what you're seeing here is the estimated target function. Okay, so the fact that you are using sample, okay, error exists. So which we're actually going to call the variance. So what we normally want to do is to minimize the two, is to start, I mean, it's actually to strike a balance. Let me tell you this. in statistics, where you are seeking when you are seeking explanatory goal, we normally like reducing bias. Okay, when you reduce bias, okay, even though you're actually going to get the truth, but let me tell you, you are sacrificing predictive power, predictive ability. Okay, but in machine learning world, we are trying to strike a balance between bias and variance. Okay, they actually going to sacrifice the truth, but they're going to benefit from high predictive power. I just wanted to take note of that. Okay, now I'm actually moving. Now, what is the main point from what I've said? What is why? I just wanted to know this. Explanatory power does not translate into predictive power. I just wanted to know that. I'm going to say that again. Explanatory power, the fact that a model has an explanatory power, does not mean that the model is going to have a predictive power. And the fact that a model has a predictive power does not mean that it's going to have an explanatory power. You cannot eat your cake and have it. And that is why you need to tell us when you are actually conducting research, when you want to embark on research, you need to let us know. Do you want to explain or you want to predict? Okay? When you want to explain, we're gonna advise you to use explanatory statistical model. But when your goal is prediction, where we're going to ask you to use machine learning algorithm. Okay. Now, I said another point. Model building is very different depending on whether you want to explain or predict. So that is what I just said. And I said, okay, I wanted to get this. Models that predict well may not have useful interpretations. And that's why when you look into machine learning algorithm, you want to talk about the random forest, you want to talk about um, neural network, you want to talk about deep network and so on like that. Okay, they actually going to predict well, but they don't have useful interpretations. But do you know that explanatory statistical models have useful interpretations because it is transparent? There's a lot of transparency. Okay, the estimation of parameters have meanings. You want to talk about marginals, you want to talk about average effects and stuff like that. So models that predict well may not have useful interpretations. And let me also say this. Models that explain well may not have predictive power. And that is the main point. Okay, so moving forward, how do we now balance interpretability with predictive power? Okay, you know, I know my statistical explanatory models are interpretable, but how can I actually also make statistical models to have some predictive power? And that is why we are actually doing this course that we call statistical machine learning, which is the combination of statistical rigor with the flexibility of machine learning algorithm. And this is the way out. If I want to balance interpretability with predictive power, the very first thing I'm going to do is to start simple and build complexity gradually. What do I mean? Okay, I'm actually for first begin with a simple interpretable model like statistical model. Okay, and after doing that, then what I'm going to do is to now build the complexity or after achieving that. So it means that the complexity will now be introduced only if it's actually going to yield what I call substantial predictive gains. But that is after you have started simple. Another way we can instigate a balance between interpretability and predictive power is the use of regularization techniques. For those of you that will be taking 4052, okay. 4051 is a prerequisite to 4052. You're actually going to focus more on supervised learning, where you have ridge regression, lasso, elastic nets. Those are the techniques that can be used to regularize. Okay, so the regularization will provide us a control way to add complexity while we are also preserving interpretability. How do I actually have a way, okay, to add complexity into my model? Because my model must not be too simple. And if I had complexity, if I had more variables to my model, how am I going to caution myself? How am I going to regulate that in order not to, or run into another problem of overfitting? And that is why we need regularization techniques like lasso regression, like ridge regression, like elastic net, and so on. Another one is to talk about the trade-off. Recognize that there's a trade-off between model families. When I say trade-off between model family, we got some models that are highly interpretable. If we want to talk about models that are highly interpretable, we talk about linear models in statistics, okay? Or additive models, or you talk about decision trees. But we also have some models that are highly predictive, okay? Models that are highly predictive. You want to talk about random forest, gradient Bayesian neural network, and so on like that. Okay. So you have to recognize the fact that, there's a trade-off between model families. Some models are highly interpretable and some models are highly predictable or predictive. Okay. So what I'm going to say here is that model choice should reflect whether explanation or prediction is the primary goal. Now, the next that I'm actually going to talk about is to train a complex model with high predictive power and then fit a simpler interpretable model. Okay? You can start with that as well. And you can also incorporate domain expertise. Okay? Incorporating domain expertise, I want to believe, can improve both interpretability and prediction. By what? By informing your variable selection. You don't just select variable into your model. You use your domain knowledge, the domain expert knowledge. And that's why you need to, you can review literature to be able to know what are the variables that I'm actually going to have in my model. So expert knowledge can substitute for model complexity. I'm going to say that again. Expert knowledge can substitute for model complexity because with your expert knowledge, you don't just put variables into, add variables into a model because without expert knowledge, you are likely going to add a nuisance variable into a model that may be problematic to the model. And lastly, hybrid models. Now, let me tell you this. When I say hybrid, okay, the hybrid models is the combination of statistical rigor with the flexibility of machine learning. That's what we call hybrid. And that is the current research that I'm doing. Okay. And of course, I've seen, research where they combine with that, you'll be able to combine interpretability with predictive power. Okay, I've seen some research article of late where they use generalized additive model with machine learning. Okay, I remember what I presented in the last spring at a seminar in our department where I actually combine statistical approach with machine learning algorithm. Talk about the learned bias generalized Gaussian mixture model. Okay, and apply that to cancer data. Okay, so the hybrid models is actually also going to work. So hybrid approaches will leverage the structure for interpretation and flexibility for prediction. So what is the takeaway before I go? Okay, balancing interpretability and predictive power requires, you uh, to actually you can choose to start simple and build complexity. You can use regularization technique, you recognize the trade-off, you can actually consider incorporating domain expertise knowledge, and not only that, you can consider the hybrid models. Is there any question before I go today? That's all I got for you. Is there any question? Is there any question before I go today? Okay, so in the absence of question, we're gonna return to in-person teaching on Monday. Make sure you all stay safe, stay warm. The weather is extremely harsh. Okay, have a good weekend. We're gonna see you again on Monday in person. Bye for now, everyone. Thank you too.
Thank
Yeah,
you.
you're
Thank
welcome.
you.
You're welcome.